So let's extend this further to a slightly more complicated design. Let's use that soy data set that we did a few weeks back when we first got into one-way ANOVA. Right, so we'll import this data set. And remember that we have two variables here. We have type of soy meal consumed and the sperm count for each participant. So participants either had no soy meals each week, or they had one soy meal, four soy meals, or seven soy meals. After a year, the researchers recorded sperm count. So we have one independent variable, which is the number of soy meals consumed, and the dependent variable is sperm count. The IV, again, is categorical, and the DV is numeric. So with no violations of our assumptions, one-way ANOVA would be best suited to answer these research questions. Essentially, is there a difference in sperm count after eating a certain number of soy meals each week? All right, so the first thing we're going to do is perform that one-way ANOVA. In Stata, that command is simply ANOVA. Again, the DV sperm count followed by the independent variable soy meals. Just like with the t-test above, I'm not going to go into detail how to interpret this table. We really just want to compare the F and the P value that we see here compared to the Kruskal Wallis test, which is the non-parametric test. For this example, we have an F ratio of 2.64 and a non-significant p-value. So our p-value here is 0.056. You might say that this is marginally significant, but it does not meet our criteria of being statistically significant. But let's test some of the assumptions of ANOVA to determine if maybe the distribution or the variability is influencing this non-significant result. So we'll first look at the frequency distribution, and we want to see the distribution in sperm count at each level of number of soy meals. So the command histogram the DV sperm count by soy meals. Just like we saw a few weeks ago, the DV is not normally distributed at any level of the independent variable. They are all very positively skewed, right? Some look very leptokurtic, some are platykurtic, and we also have an outlier here. Therefore, the ANOVA that we just did, which is comparing the mean sperm count at each level, might not actually be the best way to represent the data or represent the differences in the data. So rather than the mean, the median might be a little bit more representative or more insightful. Let's also assess homogeneity of variance here. Again, the command for Levene's test of equal variability is ROBVAR, the DV by the IV. The result of the Levene's test is significant. The p-value is less than 0.05, which we would conclude that there is a significant difference somewhere between these four standard deviations. Just like with any other ANOVA, in this case, we don't know where that significant difference is, but we can reasonably assume that the 7 soy meal group is driving that significant Levene's test. It looks like the standard deviation in sperm count for men who had 7 soy meals per week is much smaller compared to the other three groups. Now we can also see that we do have a balanced design here, right? So the design itself is balanced. That's not something that we have to worry about, but the fact that the distribution itself is not normal at any level, and we're violating the assumption of homogeneity of variance, a non-parametric test might be best. So it might be best to use the median as a comparison or the rank sum as a comparison rather than the mean. The non-parametric test we're going to do instead of a one-way ANOVA will be a Kruskal Wallis. Again, this is just the analogous non-parametric test. So if you have a design that would best suit one-way ANOVA, but you're violating assumptions or have a really unequal sample size, the Kruskal Wallis will be your non-parametric test. The command is kwallis. Just like before, we have our DV sperm count by soy meals. So for this example, we're not actually given the expected rank sum, But that's not such a big problem for this example because we have the same number of observations at each level. For that reason, the expected rank sum would be exactly the same for each level, right? So before, in the previous examples, we had very different sample sizes, which would influence the expected rank. In this case, we have the same sample size at each level, which means the rank sum should actually be equal. In fact, if you wanted to calculate the expected rank sum, you could do so using that formula I showed you earlier, but that's not necessary because we still are given all the information we need to conclude if there is a significant difference somewhere. For the Kruskal Wallis test, the test statistic is a chi-square. And again, we have an associated p-value that will compare against 0.05. Now, you should be interpreting the chi-square test with ties whenever you do a Kruskal Wallis. Again, that's just adjusting for observations that have the same rank. What you'll notice here for this example, though, is that the chi-square value is the same for the test that does adjust for ties compared to the one that doesn't. That simply means it appears that no two men had the same exact sperm count value. So for this example, doesn't really matter which one you report, but it's good to be in the habit of just reporting the chi-square with ties. All right, and again, we'll compare our p-value against 0.05. For this example, it is significant. While the one-way ANOVA was non-significant, the Kruskal Wallis is suggesting there is a difference somewhere between our levels. Just like with the one-way ANOVA, though, this can't be our last step. We can't make any assumptions about where the significant difference is. This is simply stating that somewhere the ranks are significantly different than what would be expected. So we will have to do secondary analyses, just like we do with the post hoc analyses after a one-way ANOVA. Right, specifically, we're going to do what's called a Dunn's test. Now, in order to actually do this, you will have to import a new package. Dunnett's test is a user-written package, so it's not installed whenever you open Stata. You do have to install it yourself, but it's really simple to do so. All you have to do is run the command search done test. And then what you'll do is open the most updated Dunn's test and click here to install. Only takes 1 second, and now we're done. If you were to run the command done test before doing that, you would get a user error. But now that we've done so, the command done test, the DV sperm count by soy meal should work. Should give us that post hoc test. This command will print out all possible comparisons. So the first row for each of these groups is the Z statistic for the comparison between no soy and one soy. Next is the p-value, and we have the same for all possible comparisons. So we have the z-score in the top row and the p-value below. It does say here that it's column mean minus row mean. However, that's not actually what it's doing. With the Dunn's test, it's not comparing mean differences. It does give us a z-score for the rank sum difference. You'll also notice that Stata is telling us it doesn't make any adjustment for the p-values here, which means if we just compare p to 0.05, we might be inflating that type 1 error rate. We might conclude a significant difference even if there isn't one. And this is especially important because a non-parametric test can often be a little bit more liberal compared to a parametric test. Consider the result of the one-way ANOVA we did above. That was non-significant, but the result of the Kruskal Wallis, the non-parametric test, is significant. So you can either look at these p-values and compare to 0.05 without making an adjustment. If that were the case, we would conclude that the no soy group is significantly different from the 7 soy group, and that 7 soy is different from 1 soy, and that it's different from 4 soy, because the p-value here is less than 0.05 for all 3 of these comparisons. But if you want to be more strict or more confident in your results, you could use just a Bonferroni adjusted p-value. Since we didn't have any planned comparisons, and because we've done 6 actual comparisons here, We can adjust the p-value by dividing the alpha of 0.05 by 6, the number of comparisons. So if you calculate that new p-value, the new cutoff p would be 0.008, which is quite conservative. So now if we compare our obtained p to the Bonferroni adjusted p-value, we would conclude that only the group who had 7 soy meals is significantly different from the no soy group, because this group has a p-value of 0.005, which is less than this new adjusted p-value, whereas the other two are still greater than the adjusted p. So we still might conclude that it's not a significant difference between soy meal as well as 1 and 4 soy. And remember, when you report the results of a non-parametric test, you cannot conclude in relation to the mean differences. You would simply state that the group who had 7 soy meals had significantly smaller sperm count compared to the no soy group. But you can't report means and you can't make assumptions about the mean difference in the population. So, this brings us to the end of our non-parametric practical. We have spent the majority of this semester using parametric tests, and that's because they're much more widely used. It's a lot more practical to make comparisons to the actual means themselves, but it is still really important to understand how to treat your data if you are violating assumptions, if you have unequal sample sizes, and if you have really extreme outliers that you don't necessarily want to remove from the data set, but you also acknowledge that it heavily impacts the mean. So now we've gone through 2 examples of how to do non-parametric tests, but again, there are other types of non-parametric tests that you should know how to use, such as the Spearman rank. So if you do have questions, you should ask your tutor as soon as possible. Other than that, have a great week.